Hello, students. I'm going to try to give you a little overview of how Prolog works and logical programming in general. Hopefully, this will be complementary to all the material you have, and I'm hoping this can help. So let me start by saying we'll use a little program here I wrote as an example, but before we get into Prolog as such, let me start by saying, giving you a little bit of background in terms of what the field of resolution and solving problems in logic in general. Just so you know, you've probably heard of propositional logic, like propositions like A or B, things like that. We can solving this problem is called the satisfiability problem. Is quite simple. It consists in figuring out what are the truth values of A and B that are such that this whole proposition is true, right? So here there are multiple. You can have A is true or B is true or both are true. In these three cases it works. In these three cases it works and it's satisfiable. Okay. In this field in general, you have to be aware that it's important to understand that problems are very, very hard to solve. And in general, they are just intractable problems. So if we take, what I mean is that if we take any kind of logical proposition of any arbitrary size or style, it will take an exponential time to solve. Why? Because so if we take a proposition only in the form of what we call clauses, the closed normal form where you have a disjunction, so only ors like that, say A or B or not C, and A or C and B or not D or C or E, say something like that. So these are clauses separated by so clauses are only disjunction and they are all joined together by conjunction, so and, right? So you have only ors within the parentheses and between. Anyway, you can translate actually any kind of proposition into a closed normal form like that. These are in general very, very hard to solve. They are considered to be very hard problems, and this is something you'll see in the course 475 on the topic on complexity. So they are very hard. Why? Because eventually, to decide what combination for A, B, C, D, E will make this satisfiable, you have no other choice than just test all the truth values. So it's an exponential time to solve that. You're going to have to test A is true, B is true, C is true, D is true, E is true. And then the same thing with E false. And then the same thing with D false, etc. And you have to test all possible combinations until you find something satisfiable. So in the worst case, it takes a very long time. So I just want to mention that as a background. It is very hard to solve logical problems. Now, Prolog does it in linear time. It's actually really, really fast. And to do that, they kind of put a constraint on what kind of formulas here are allowed. Only a subset of those are allowed, so that it can be doable in not in exponential time, but in linear time. And as you'll probably experience, Prolog is surprisingly fast, actually. So we'll go back to that, but that was a parenthesis. Okay, so now. Let's dive a little bit into. So I built this tiny little program based on living beings in my household, including people and pets. And there are some facts here, some rules here, and we'll dive a little bit more into that. So just gonna dive in here. Sorry, and just start SWE. Here, so SWE is a standalone application. It's very easy to use. I go to File, Consult, to consult my my file here, you can also use console bracket quote and file.pl, you know, I mean the name of your file.pl. I mean you have to put the whole path actually here and a dot here, and if you press enter it's gonna work, but you can also use the menu. So I can ask, you know, who is logical in the household, basically, you know, who has the age of reason. I can ask things like, you know, what are the pets, and I can ask, you know, living things as it's without an S. So here are the living things. I press semicolon every time I want to have another answer, and I can ask a little bit more complicated things. You know, I can ask, you know, I can use the find all built-in query, say find all x such that x is a living thing, and put that into the list of living things. And here's my list of living things. You can also query binary predicates. That means predicates with multiple, not just one, but multiple arguments. Again, ask, you know, what does Jean you know, owns. I can use the variable owned by Jean, and Jean owns Hopper and Tabitha. Okay, so that's quite simple. You have tutorials I suggested that can help you with this piece. It's really not necessarily the focus of this presentation. What I would like to talk about is more how Prolog is organized here, and what are these, and how does this work. You know, a little bit of looking under the hood of Prolog and logical programming in general. So Prolog, so it's basically consists in a program, right? You have a .pl file, and this file is composed of you will notice a series of facts and rules. And so you have here, the way I organized is I started with the facts and then I put the rules. I could have done it differently. Of course, there's no really order here. I mean, it doesn't really matter. It's just for an organization point of view. And it happens that all of these facts and rules are all what we call in logic horn clauses. So they are a specific kind of clause. So I said, you know, this is a clause. What is a clause? A clause is a disjunction of literals. So this is a literal, this is a literal, and this is a literal, right? The literal can be positive or negative. This is a sign of the negation, right? So a literal can be positive or it can be negated. So positive, positive, negative. This is all positive. This is positive, negative, positive, positive. Okay. So a horn clause is a special type of clause. So clause is always a disjunction. It's only ors, right? So it's very poor, right? With horn clauses, you cannot express so much. I mean, with just clause, you cannot express so much. You need to put them together with ands so that they are more meaningful. But here, our program is only composed of horn clauses. A horn clause is a clause that has 0 or 1 positive literal. And we'll see what that means and why it's the case. But I'm just going to give you a little looking ahead. This is the reason for that is that this solves the problem we mentioned before. If you have only 0 or 1 positive literal, which is actually not the case in any of those, there is a way to solve the satisfiability problem, right? The problem that which consists in finding a solution such that this is satisfied. That makes it such that we can have an algorithm, a linear algorithm to solve it, and therefore it's not exponential and not untractable. So that means that the solution can always be found in a reasonable amount of time. So we can find a linear resolution process for the satisfiability problem. So that's why we impose that condition, 0 or 1 positive literal. And we'll see a little bit more about that. Okay, so if you have 0 or 1 positive literal, just let's take the case of 1 positive literal. What does it look like, right? You're gonna have something like A, or let's say instead of B here, A or not B, or not C. Okay, and this actually can be changed into using the basic rules of logic into A or not B and C, because not B and C is the same thing as not B or not C. And we have another rule that says you know, if you have somewhere, you know, A implies B, it's the same thing as not A or B. This is something really convenient to know by heart. A implies B is the same thing as not A or B. So here you have not B and C or A. So that means you could actually replace that by B and C. Sorry, and C. This is an and. Implies A. According to that rule, this is the same thing as this, right? So all of these are the same thing. And now let's invert, right? And write the arrow the other way around. So instead of saying B and C implies A, which again is the same thing as this Horn clause, right? That has only 1 positive literal and 2 negated literals, right? Instead of saying B and C implies A, I'm saying A is implied by B and C, right? It's exactly the same thing, right? I should keep the parentheses to make this clear. They go together, and or you can say A if B and C is the same thing, right? If you say A is implied by B and C, or you can say A is true if B and C is true, right? It's the same thing. And now we have basically here our Prolog schema in some sense. I mean pattern, which is going to be A, the Prolog neck, and then we replace the ends here by commas, B comma C. So when you have in Prolog, like here, you know, logical X with the neck, and then a list of propositions, this is really what this means, right? This means, you know, if X is a person and A is the age of X and A is greater than 6, then X is logical. So that's how you can read. I mean, it's convenient to see that because that's really the meaning of these Prolog rules, and that's how you can read them. It's not really convenient to read them as Horn clauses because this is not as intuitive to say A is true or not B is true or not C is true. It doesn't, like, cognitively doesn't have the same, it's not as clear in our mind than when we say B and C implies A. This one is the most, I would say this one is the cognitively the most meaningful for a human being. So that's why also Prolog uses that one. It's not just because Horn clauses are convenient for a resolution perspective, but also because it actually is easy to read, right? So you can either read them, here, you know, the way I did it, you know, if X is a person and X is, A is the age of X and A is greater than 6, then X is logical. Or you can read them linearly the way it's written in Prolog, which is X is logical if X is a person and da 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 da. Okay, so these are basically just Horn clauses, right? These are all Horn clauses because they always have one positive literal and then negative literal, and we'll see why 1 or 0 and why not 2 and more. But just so we're clear on the terminology, so I call this this is the neck, the prolog neck. This is what we call the body and the head. So you have the head before the neck, which is kind of makes sense. The neck and the body, it's kind of a good, it kind of makes sense because you notice that the A, what ends up being before the neck when I did my translation, is the only positive literal, right? Because we cannot have more than one, we are at most one positive literal. It kind of makes sense to call it the head because it's unique, right? There's only one always on the left of the neck. And then on the right, you can have a list as long as you want, right? There is no condition on the horn clauses of the negated literals. You can have as many as you want, right? You can have very long rules. So the body is plural and the neck is unique. So it's kind of a really a neat terminology, and this is the neck. So okay. Now, what about the facts, right? We have facts here. Facts, they don't have this, you notice they don't have this shape. Let me write one of the rules here, just so we can see more clearly. So I said logical X. So we have here the head, and here I use only what we call propositions. So they are just true or false. Here it's the same thing, right? Logical X is true or false. Now this is not just it's more precise than what we call proposition logic. It's what we call predicate logic, because a proposition is not composed of a predicate and a subject, and it is true only if the subject falls under the predicate. Okay, so it's just a sort of a how to say that, enrichment of this, right? With more details if you want. Okay, so here is our example was person X, and so you have here again the head, the neck, and the body. I put the body here in one line, but it's fine to put it in several lines in Prolog. The Prolog is very, very permissive in terms of the way you organize things. It's only the punctuation that matters. Talking about punctuation, let's not forget the dot here that ends. I forgot it here. That ends are horn clause, basically, right? So a program here is going to be a set of horn clauses, right? We have here several rules. We have one rule here, another one here, another one, here. I mean, we have multiple rules, right? Each rule is a horn clause. So basically the dot is separating each horn clauses just the way the and separates horn clauses here, right? So our program is not going to be just one horn clause, which would be very weak in terms of expressivity. It doesn't mean much. I mean, you cannot do much with it. It's a set of horn clauses separated by dots, and they are basically they all have to be true. So they are all separated by and to constitute what we call the closed normal form that basically has the same kind of expressive power as logic in general, where you can have and or implication and stuff. So so the dot is separating all the horn clauses are brought together by as conjunction, basically. Okay, so these are the rules. Now we can ask, what about the facts? Well, the facts, I'm gonna just write one from here. Like we have the fact that Tabitha is a cat, for instance. It's here. So cat Tabitha is a fact. Well, this is actually also a horn clause, except it's one that has no negative, that has no let me rephrase that. It is one that has no body. So yes, no negative literals. Okay, so you basically don't have the part after the neck. So you don't need the neck. You just put just the head. So it's just the head, right? So if you translate that, if you follow the same, this is basically just the A, right? A is true, A is true, A is true, A is true, A is true. You end up with here without the B or, the not B or not C. So you end up without this piece. So you just have A. So you have the head without the neck and the body, right? You still have the dot at the end, very important to separate from other clause. That's what a fact is. You're just saying Tabitha is a cat. That's a fact. So it distinguishes it from the rules. So again, this is the head, and there is no body. So these are headed horn clauses. These ones and these ones, the facts and the rules, because they have one positive literal and possibly zero or any number of negative literal. If it's zero negative literal, it's a fact. If it's one or more, it's a rule. This is what we call a rule. Now, we said that a horn clause could possibly have zero positive literal. That means zero positive literals. That means it has no head. That's what we call headless clause, right? So what would a headless clause look like? Well, a headless clause would be basically the neck with no head, no positive literal, and only negated literal on the right? So it would be, B, C, D, E, for instance, right? You have just a body and a neck, no head. So in terms of horn clause, it would be, this one would be, not B or not C or not D or not E, which is, according to our definition of horn clause, perfectly fine, because the definition says you have either 0 or 1 positive literal. Here we have 0 positive literal, so that's perfectly fine, and we have 4 negated literals. Where do they fit in this picture, right? So so just the same way that you can read this as, well, it's the head, so there is no body, so there is no if condition, right? It's not A, if, B, and C. It's just A is true, right? Tabitha is a cat. That's just true. There's no condition for it. Here it's kind of the opposite. It says, I'm giving the condition for what? What is important to understand is that a Prolog, if this is a Prolog program, what completes it is another piece that is important to not forget, that is the queries. And the queries are these headless clause, right? So basically, if you replace here the colon by question mark, you have here the symbol that we have on SWI here, right? Question mark dash to that asks us for a query. So when I put question mark dash pet p, I am basically giving to Prolog a headless clause that is going to be checked against the whole logic database. Okay, so so that's something I wanted to mention, that this is our logic database. Okay, constituted only of this kind of headed clause, right? And query is going to the query is going to be checked against the logic database with one of these headless clause. So you basically going to, like here, query is always consisting of a series of literals, that look actually positive, but the way they're going to be translated is going to be translated into negative littles, um, because that's what they actually are essentially, right? And the query is going to be checked against the database to see if it is satisfiable for some instantiation of the variables you give, right? So here when we say pet p, what Prolog is going to do is going to check, and that's what it did. What are the instantiations of p that make this true given what we have in the current database? Okay. So it's important to understand that Prolog, it's both a program, a .pa file that is our logic database constituted of facts and rules, and the queries. The queries are important. The program in itself it's a knowledge base, but it's not going to run on its own. And that's a very important piece to understand, right? You cannot just execute a Prolog program. It won't do anything until you actually query it. So these clauses complement these, and together they can execute a satisfiability request to check is there a way to satisfy these. And because we are only limited to horn clauses, it's much easier. And I'm gonna try to give you a little taste of how it works, how the process works, without getting into the details. But basically, and to give you an idea of what makes it kind of linear, right? So when I ask to Prolog, what are the logical things? Oh, sorry, it's not working properly. Okay, logical x. It gives me x equals Lauren. So how is Prolog solving this this goal? And actually the headless clauses, we also call them goals. So it's considered as a goal to be satisfied. I want to satisfy x is logical, x being a variable. So I'm going to find some instantiation of x that make this logical true. So the way it's going to work is that Prolog is immediately going to look in the database and really like an index database. It's just going to go line by line. I mean, horn clause by horn clause, which, it's not necessarily line by line because this horn clause is on multiple lines, but it's going to check each horn clause, facts and rules is indexed. And it's going to take the first one that has a predicate logical, right? So these are not the predicate logical, so it's going to stop at line 58. This is the predicate logical. So now that is the goal I want to satisfy, is logical x. So if I had put actually some other variables here, that would have been more interesting because now it would kind of unify that variable, let's say y with x, and now let's satisfy logical x. And the way it works is that now it's the goal is transformed into 3 sub-goals, 1, 2, 3, and these 3 sub-goals are going to be linearly one by one satisfied. So first I'm going to try to satisfy person x. So person x becomes my goal to satisfy. So if I put person x here, it's going to also work exactly the same way as what it does when person x is taken as a sub-goal to satisfy. So what does it do? Well, again, it goes back, and really that's how it works. It goes back to the beginning of the file and look for person x. Well, actually, the very first fact is the right predicate. It's person. So Lauren is a person. So now x is what we say unified with Lauren, right? So we consider the Prolog is considering x equals Lauren. And it's not yet validated. We're not yet there where it displays x equals Lauren because it's not finished, right? But it's satisfied this predicate. Now, age x A is going to, now we have X is unified with Lauren, so it's actually going to look for age Lauren A. So same thing, goes back to the beginning and it's going to stop at line 36, age Lauren 37. So A is going to be unified with 37, right? And now this goal is successful. These two goals have been successful, right? Because we found a way to unify variables that makes it successful. And here we don't even have unification to do because A is already defined, it's 37, but it is just a proposition that has to be true, right? For this, the goal to be satisfied here, all the sub-goals have to be satisfied. Because again, each of these comma represents an end, right? Remember the comma on the right is equal to an end logically, right? So A greater than 6 has to be satisfied. It's the case, right? 37 is greater than 6. So the third goal is satisfied. So the super goal, if you want, the overall goal is now satisfied. And so because it is, and it was my goal, X is now unified. I mean, is now X equal Lauren is offered as an option. Now, and this is an interesting thing. I don't know if you noticed, but we have no way to express on the left side the notion of or, because we have only at most one head. We don't have multiple heads. So I cannot say something like B and C or A or D. And I cannot add other options here. Well, the way the or works, and it's a bit tricky, but it really works within the calls through query. So here, if I hit the semicolon, which is equivalent to an or in the logic of Prolog on the left. So in some sense, what I could write is that the way we could write this down is that logical X is true. So that's, again, that's our kind of like our headless clause here. And we can now, in some sense, we ask Prolog to find the head to this headless clause, right? So logical X is true if X equals Lauren. But now we the semicolon here that I'm putting on the terminal is basically asking, well, find me another X such that this is, you know, that such that logical X is true. So you can think of the semicolon as an or, and now it gave me another one, gave me Hugo, and can give me a bunch, right? But at some point it's gonna end up with no more answer, and it's just gonna stop because it's over. Some other Prolog interpreters, instead of stopping, will tell you no, there's no more answer. Will give you a no answer when you put the last semicolon. So anyway, what don't worry too much about semicolon. That's kind of something that's a bit more complex to grasp. But what I really wanted you to understand is how the resolution works, and in some sense just have an idea of the linearity of it. I do not have to check every possible combination of truth values like I would do here. I do not have to check every possibility. I just have to take them one by one. You know, if I have a query with multiple propositions, the way I have it here, right? It would be like this, for instance, you know, I want X to be logical and X to be also a pet. That's what it would mean, right? So now if I hit enter, it tells me just false, right? And the process it went through is exactly the same, right? It went through the process of, okay, I'm going to find a logical person. I'm going to all the way down. It's going to find Lauren first, and then it's going to try to unify Lauren with the pet. But the problem is that the pets can only be satisfied, so it's going to try to look for pets, right? Once it went through logical, it keeps going, right? Because it has to satisfy both of this. And actually doing this, or here putting a rule that is called logical pets, and saying, you know, logical LP and pet LP is exactly the same thing, right? If I write this rule in Prolog and I then query logical pet here, it's the same thing as asking that here, right? Because what I find here is in the body of my rule here, right? So it's going to be the same process here. I'm going to try to unify to find an X that satisfies satisfies the goal logical X, and it's going to return a bunch of people, and then for each of these I'm going to try to satisfy the goal pet X, but none of them is going to work, so it just answers false. That means there is no satisfiable answer. Okay, so that was my little overview. I just really wanted you to get a sense of what is a Prolog program, really to see it as a logic database with facts and rules. See how facts and rules have this thing in common, that they all have one positive literal and as many as you want of negative literal, and that the queries kind of complete in the set of horn clauses the facts and rules as horn clauses with 0 positive literal, so headless, these headless clauses. So they are of a different kind, and the way they are, because they are like that, we can take them really linearly with taking each of these as one goal, and we go through each of the goal to satisfy them in a linear way. This linearity is really what is foundational. It's what we call the resolution principle. That is at the foundations of any logic programming software. This resolution principle and this linearity is the key to make logic programming possible, because if you don't have it, you're stuck with the only solution, which would be to check all possible truth values, and it's intractable. It just takes exponential time. Okay, so I hope that in all of these messy explanation, there's some things, some good takeaway for you guys. You know, just maybe the fact that reading this correspond to reading it that way from a logic perspective can be a really good takeaway to understand Prolog better. And if you have any questions, don't hesitate to reach out.